So you have started primarily in the 11th grade right now, right?
Mm-hmm. Yes.
And the starting of the physics, you might be knowing that physics is incomplete without mathematics. That's why the first chapter comes in as vectors, right?
Yes. Yeah.
So see, anything in physics, I think this is a subject where you have to give a very low input and you can get a very high output if you really understand the concepts, right? There are many situations, right? For a given topic, like for example, you are understanding projectile. There could be n number of questions that can be made out of it, but there is only a single concept on which those n number of questions are based on, right? So,
Mm-hmm.
what I generally advise people who are pursuing this course is you need to categorize the questions in your mind, that what category this question belongs to, and then you need to visit that concept, apply that concept, get the questions done. Okay.
Oh, yeah.
Yeah. So whenever you are reading a certain topic, right? For example, you are reading 2D motion, okay, which is addressing projectile. So you need to have a very clear categorization in your mind that what are the concepts this topic contains. Okay, for example, in this and this and this and this. So there are limited concepts. Now the question comes in, you categorize that question. Oh, this question belongs to this category. Apply that concept, get the question done. This is how it works. Very sorted stuff. Okay. Now to begin with, what we should take on today.
Um, right now in class we're learning about force of attraction and
Force of attraction.
yeah, like gravitational force of attraction.
Okay. So I should start with making you understand the universal law of gravitation and all those stuff, right?
Yes.
Okay. Let us start with that then. So when we talk about forces, you could see my screen, right?
Mm-hmm.
There are four basic forces in the universe. Okay. First of it is what you told is gravitational force. Gravitational force. And this is what we're going to understand today in detail. The second one is a nuclear force. Third is the electromagnetic force. And the fourth is the van der Waals force. Only four kinds of force exist in the universe. Out of them, today we are discussing gravitational force. Okay. So what do you think gravitational force is all about? It's about the force of attraction between two bodies carrying masses. Force of attraction between two bodies carrying masses. So this force of attraction is by the virtue of mass. Okay, this body has a certain mass, this body has a certain mass. By the virtue of mass, they are feeling attracted to each other. Right? Now,
Mm-hmm.
we need to, the second point is this is always a force of attraction. There is never a repulsion experienced. There is never a case where this body repels another body. They always attract. Right?
Mm-hmm.
So, for example, you have this body of mass m1, another body of mass m2. I am taking these bodies as spherical bodies for the sake of symmetry. And this particular force is also defined between the spherical bodies or point masses. Okay. So you take these two spherical bodies of mass m1, m2, the distance between them is r. All right.
Mm-hmm.
M2 will apply a force of attraction on m1. M1 will apply a force of attraction on m2. Right. This is F. This is also F. Is this force equal in magnitude? Yes. Both F are equal in magnitude, but they are opposite in direction, right? So if you are writing it as F12 and you're writing this as F21, then you can say F12 vector is opposite of 21 vector. These two are opposite. While in terms of magnitude, they are both same. You understand these notations?
Yes.
So this is a notation representing the magnitude. This is a notation representing the vector things. Now, whenever this theory was getting developed, initially experiments were conducted, right? You might have heard of that story that Newton observed apple falling, right? And
Yeah.
then this was the observation, right? After the observation comes the experimental part. That okay, if the mass of the apple is this, mass of the earth is this, that how much force? In spite of apple, if I put an iron ball, then how much force? If I put apple at a different distance, then how much force? All these questioning comes in. And out of these questionings and experiments, there comes out a theoretical basis, a formula. Because as a layman, I will not go to the laboratory and experiment and find out what is the gravitational force. I'll simply use the formula that they have given to me, right? So
Mhm.
by doing all those experiments, Inu, they find out that this force F is proportional to masses. It is proportional to M1. Also, it is proportional to M2. Okay. Larger the mass, the larger the force of attraction. So you understand this like sun and earth. Earth is moving around the sun.
Mhm.
It is not tied by a rope. It is bound by the gravitational force, right? If earth
Oh.
being here, sun being here, let's say earth stops moving, what will happen? It will simply go and fall into the sun. So, but since it is rotating, what is happening? That particular force is acting like a centripetal force, which makes it keeps on moving. Otherwise, it
Oh.
fallen into the sun, right?
Okay.
So
Yeah.
there is force of attraction. Definitely there is force of attraction. But because of that force of attraction, which we are calling gravitation, there is motion. And there's a perpetual motion. There is no battery over there, which is giving constant energy to the earth, right? Without any battery, this system is moving, you see, right?
Oh.
So the binding force is the force of gravitation between the earth and sun. It's a very large force, right? Because the mass of the earth and mass of the sun are quite significant. But at the same time, the distance between them is also significant. So this particular force is inversely proportional to the square of the distance. As for example, you have two bodies like this and this, and the distance between them is r. The force acting is F. As you make this distance 2r, the force becomes 1/4 F by 4.
Oh.
Yeah. So larger the distance, the force goes down. But what happens in case of earth? In case of earth, what happens? The object and the mass of the earth is very large. So in fact, if the distance is also large, mass being large, the force is significant. You have a significant force, right? So
Mhm.
whenever you launch rockets and all, after a certain time, when they are like quite high, the effect of gravity diminishes to zero. There is a gravity-free setup, right? In fact, people are going for trips where they experience zero gravity in the flight also, right? After a certain height. And you know what, Inika, that zero gravity thing can also be created at a normal height also by free falling, by
Oh.
falling, right? So if in fact you are, let's say you are in a lift and you are on 100th floor, and suppose the cable of the lift breaks and you start free falling, that time also you experience zero gravity.
Oh, I see.
Exactly. That time, because you are simply falling as if the earth is pulling you, you are not resisting it. That's why you are experiencing zero gravity.
Oh, I see.
But if you try to maintain that, for example, if you try to maintain to be at that height, then definitely you will experience gravity. Isn't it? So basically, whatever force is there between these two bodies, this force comes out to be G m1 m2 by r square. So I don't know whether you understand this. This symbol is a symbol of proportionality, isn't it?
Mm-hmm.
This is a symbol of proportionality, which says that if mass gonna increase, the force will increase. Then R gonna increase, the force will come down because it is inversely proportional, right? So this is a symbol of proportionality. So whenever an experiment happens, we find out that this force depends on this, okay? But at the final stage, we have to craft a formula. So when we have to craft a formula, all those proportionalities should be replaced by equal to sign. And there comes in a constant value, which fills in. So G is a constant. Generally, what happens, scientists who are working on that formula, they name the constant on their name. So they become popular. But this time, this G was named as universal gravitational constant. Universal gravitational constant. This was not named on any of the scientists. And its value is constant, equal to 6.67 into 10 raised to the minus 12. Can you help me out writing the units of this? Dimensions and units of G.
Writing the
Yeah. What should be the units? This is the value.
oh
Okay, try this way, Inika. This is G, okay?
uh,
Force has a unit of Newton. You know that?
mm-hmm.
Uh, Distance has a unit of meters. So this meter goes over here. This becomes Newton meter square. And these two have a unit of kg. It comes down. Isn't it?
Mm-hmm.
So what should be the unit come out to be? Newton meter square per kg square.
Oh,
In the formula itself, all the units are hidden. You just have to rearrange, right? For example, G is what? G is force times distance square divided by mass square. So this is Newton meter square per kg square. But a very, very important aspect is, let's say I am sitting over here and there is a chair lying over there. Now both of us are masses, right? You understand that?
mm-hmm.
So the question might arise in your mind that there should be force of attraction between both of us.
Mm-hmm.
And over the time, the chair should come closer to me automatically. And the wonderful thing is, this force of gravitation is a non-contact force. You need not to go and do a contact with that body in order to pull that body. It's acting without any contact. If you throw a ball, the earth pulls it down, but there is no contact between them, direct contact. There is air between them, right? So if I am sitting over here, the chair is over there. I am simply pulling the chair is also pulling me. But that never happens that it is apparent that we are coming closer. Does that happen?
Mm.
Why?
The Earth's mass is much bigger than the mass of you or the chair, so its attraction is.
In this case, my mass and the chair mass, they are comparable. I am talking about not about the earth. See, the gravitational force is something that is applicable to all the masses. Okay. Of course, it is relevant for the earth, but it is applicable for all the masses actually. So I'm just trying to get you to the point using these values, Inika, that why is the gravitational force between me and the chair is not significant? That is what I want you to answer. Why is it not
Okay.
significant? Yeah. let's say my mass, let's say it's 75 kgs, okay? And let's say you have a chair. Let's say the mass of the chair is 50 kgs. So M1 could be 50, M2 could be 70. But at the same time, Inika, you see G value. G value is a very less value. It is 10 is to the minus 12. You see what the G value is?
Mm-hmm.
So when you multiply both the masses with the G value, you get a significantly lower value.
Oh.
You're getting my point?
Yeah, so the
Otherwise,
force would be
everything could have come to me and I would have been unable to move. Like washing machine, everything lying over here. By the force of gravitation, I could have pulled everything, right?
uh,
But the point is, this force is significantly low and it is unable to overcome by the force of friction. So if it is trying to come towards me, there is force of friction acting on the ground, which could easily stop it. That's why you don't see
oh,
that body coming towards me. Okay.
uh,
But when you put Earth into the picture, this mass goes up. It becomes really high. It is 10 is to power 24 kg order. It's a very, very high mass of whole Earth. So it overcomes the small value of G and makes the force really significant. That's why when you throw a ball, you could see the ball instantly coming down after a while. Because that time you could really feel the gravitational force. You will never feel a gravitational force between me and another body or any body that is kept over here because it is significantly low.
okay.
Do you got
That
the
makes
nitty-gritty of the stuff?
yes, that
That is
makes a
very,
lot.
very important. So with this, I am trying to conclude that gravitational force is a very weak force in general bodies are concerned, when the general bodies are concerned, until and unless you are bringing in celestial bodies like planets, right? Big rocks, asteroids, something like that. Okay. It is not significant for us here. Like, for example, you talk about a basketball and a football, you keep them, right, at a certain distance. There will be no significant gravitational force between them until unless the mass is large. All right. So there are two important points which I wish to highlight with this discussion of ours. First is gravitational force is a long range force. It could act on long ranges. Like for example, sun and earth, they are very far away, but still the gravitational force is acting. It's a long range force. Long range force. The second point is in general, with normal masses, it's a force of lower magnitude. The magnitude will be respectable only when the masses interacting are large, or at least one of them is large. Okay. So it is a weak force for masses of normal magnitude. Is it clear till here?
Yes.
Now, I will like to know, this is a general introduction that I have given along with the formula, how it is acting and all. Now, in your textbook or whatever your coursework that is going on, uh, how is it addressed? What are the questions that we need to solve on this? Can we have some of those questions?
Yeah, let me check
Yeah.
somewhere.
You can send it to me on the chat of the Zoom also, those questions, and then we
Okay.
can have a discussion over that. So whatever we study should be relevant to your coursework.
Yeah.
Yeah.
Let me pull it up quickly. Let me copy paste one of the problems.
Okay, all right. So you have sent it to me. Okay. That will also give me an idea that what should be the course of the lecture. So you have sent it to me on the Zoom chat or what?
Not yet. I need to. I'm actually copy and pasting it from the.
I think the Zoom chat also allows taking screenshots. You see,
Oh,
the chat has that option. Uh, when you go to the
oh,
chat, right? There is a chat written over there, right?
oh yeah.
You open it. There's a screenshot option, Inika, over there
Oh,
near the
oh,
send sign. You see, so you can take a screenshot of the screen and you can directly send it to me.
okay. Alright, here's a screenshot of two questions that we have.
Sorry.
This is a screenshot of two questions
Yeah,
on the thing.
I think it is loading right here.
Okay.
Okay, so it is let me open this. Okay, let me take it over here. We have sent it over here. So it's come into the chat section. All right, these are the questions, right? Two physics students sit 80 centimeter apart. Their masses are itna. Wow. Now this is something that we were referring to, right? So let's do this question by yourself. Like, so what's the formula that you're gonna use? F is equals to G times M1 M2 by R square. What is the G value?
6.67 times 10 to the negative 12.
Yeah, you can put that value over there. Multiplied by 42, multiplied by 58. All right.
Mm-hmm.
And divide it by 80 by 100 square. Isn't it? Divide that value with 80 by 100 square.
Oh,
Does that seem correct to you?
yeah, yeah.
Yes. So you could see yourself that what a small force this is coming out to be.
Yeah.
Crop. All right. So this is coming out to be a significantly small force. Oh, 6.67 into 10 is to the power minus 12 into 42 into 58 divided by 80 by 100 square. Is it fine?
Yes. 1 second, sorry.
So you could solve it now. Like we have already constructed the formula. And you are aware, Inika, that 80 centimeter is a CGS unit. So in order to place it into the formula, you have to convert it to meters.
Mm-hmm.
This is what you are aware of?
Yes.
All right. All right. All right. Then what is the next problem? Wow.
Mm.
Protons, neutrons separated by a distance this much meter if the masses of the two particles. Now you could yourself see Where is this proton and neutron thing comes in, Inika? Proton, neutron. Where is this thing comes in? When you understand the structure of
The atom.
atom. Exactly. When you understand the structure of atom, right? This becomes really significant when you further go into the nucleus, because neutrons and protons are present in the nucleus. They are not present outside.
Yeah.
Outside there are only electrons, isn't it? So, you see, protons and neutrons both have certain masses. They are inside the nucleus. What is the real challenge inside the nucleus? Can you tell me that? What could be the real challenge? This is the nucleus, let's say. Okay. And nucleus has got protons. You know, protons are positively charged. They are there. Then they have got neutrons also. They are neutral. What could be the real challenge inside the nucleus that you are facing? Do you have an idea that positive charges repel each other?
Yes.
So the real challenge is bringing those positive charges together,
Oh.
because those guys are sitting very close and they are always fighting because they try to repel. So the stability of the nucleus is a big deal for us. How can we make this nucleus stable? It's a very big deal for us. How can it be made stable, Inika?
By adding another.
See, what do I want? I want protons and neutrons to stay together. But protons are trying to get off because they are positively charged, right? Now there is an option, the force of gravitation. The force of gravitation should make them attract and come closer. The gravitation is also acting between neutron and proton, no? Proton and proton. It is a force of attraction. It is not a force of repulsion. That is why they have given you this question. You calculate the force of gravitation. When you will calculate the force of gravitation, Inika, you will realize that it is a very, very weak force because the masses are too small. You see, what are the masses? They are of the order of 10 to the power minus 27. So what the force will come out to be? Let us calculate. You tell me the values, I'll put them. G value 6.67 into 10 to the power minus 12. Okay. Then you have a proton value 1.67 into 10 to the power minus 27. Then you have a neutron value 1.67 into 10 to the power minus 27. Divided by, my God, 1.2 into 10 to the power minus 13 whole square. So you could get a force which could be as least as possible. Because even this 10 to the power minus 13, it will come up. Though it will cancel out one of the powers, you see, it will become 10 to the power minus 26. Here you have 10 to the power minus 27. So it will get partly cancelled out, but still it is a very, very low force you are getting over here. And this low force cannot hold the nucleus together. That's why you need nuclear force. Okay. So in the very beginning, I told you there are four forces: gravitational force, nuclear force, electromagnetic force, and van der Waals force. So nuclear force comes in and it holds the protons and neutrons together. It is a very, very larger force because it is trying to hold them together. Otherwise, if we would have betted upon the gravitational force, the nucleus would have simply exploded. The gravitational force is not capable to hold the nucleus together. Making sense?
Yes.
So I think we addressed both of these questions that way, right? Anything else? Questions or theoretical part? I mean, this chapter might be like, there must be other things also in this chapter, right?
Other things, yeah, we haven't gone to that yet. I think Most of the questions might be like this.
Okay.
Um,
Or any other subtopic which needs an explanation apart from what's the force values.
this one's interesting as a graph. I'll do this question quick.
All right. So here comes in another screenshot, right? What that screenshot is saying. All right. Wow. Okay. So as far as I know that you also have labs over there, right? And you do some practicals. Do you have
Yes.
labs?
I one lab.
They take
Not
you to
sure.
the laboratories to do some experiments in order to get the results derived.
Yeah, yeah. Yes.
So every chapter you go to a certain lab, there are certain assignments designed for the lab, right?
Mm-hmm.
This is the one that you have sent to me. The first question, that is more of a experimental nature question, you see, Inika. Why I'm calling so? Okay, now let me make you understand a very, very important concept regarding the G value. What is this G value? Small g. This G different than the one that I have taught you right now, the capital G?
Mm-hmm.
Is it different?
Yes.
Yes. What is the small g thing?
Gravitational field strength.
This small g. Capital G is gravitational force constant, universal gravitational constant, no doubt about that. But what this small g is?
Is it like the field strength? Is that what it's called?
Just can you repeat what you're saying?
Field strength?
Can you write it
Or
on the chat what you're saying? I'm
yeah.
unable to get the words.
Uh,
Oh, wow. What a word. Gravitational field strength. Yeah, yeah, yeah. Very true, very true. But to me, it sounds a very jargon word to me, like gravitational field strength, a very hi-fi word. Can it be made simpler, right? In order to get a feel and understanding. Okay. So, Inika, what is the G value near the surface of the Earth? What is the value of this G near the Earth's surface?
9.8
Very good. What is the units?
meters per sec or
9.8
newtons over kilograms.
meters per second square. This is what the unit,
Oh.
isn't it?
Mm-hmm.
And generally, what you called it, gravitational field strength is the right thing. But in order to simplify, we call it acceleration due to gravity.
Oh.
We call it acceleration due to gravity. You know what acceleration is, Inika?
Mm-hmm.
It is a parameter which causes the changes in the velocity. You are driving a car and you hit the accelerator, the speed and the velocity increases. And the increment in the velocity is governed by this parameter called the acceleration. Acceleration has got the unit of meter per second square. So I want to break this down for you and help you understand this in a deeper detail. Your acceleration is being told to be 9.8 meter per second square. All right.
Mm-hmm.
In reality, what does this mean? Let me help you explain. Can I write it like this, Inika? 9.8 meter per second per second. It can be written
Mm.
like this also.
Yes.
So now this is indicative of the fact that let's say this is Earth. And all around the Earth, the gravitational field of the Earth is present. How come I know? Because if I leave any object somewhere near, Earth tries to pull it. So the impact of the Earth is present all over. And that impact is defined in terms of gravitational field strength. It is not visible to us. It is an imaginary concept which scientists have introduced in order to understand the effect of the gravity, isn't it?
Yeah.
So let's say this is Earth. Everywhere in the surrounding, the impact of the Earth is present. But you know what? A wonderful thing, that G value is diminishing as we are approaching farther from the Earth. Is it like that?
Yeah.
So it's very, very similar, Inika, that let's say you have a mayor in the town, right? The influence of the mayor is restricted to the town, right? As you go out of that town, nobody knows him. As you go farther, 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 isn't it?
Yeah.
The same way, the gravitational force is much higher near to the surface of the Earth. As we go farther from the surface of the Earth, it goes on diminishing. That is what is
Uh,
getting reflected by this graph. You see, it's a diminishing graph. So they have made Earth at the origin, isn't it?
mhm.
And at the origin, you see the gravitational force is maximum, which is coming down. At the surface, it is maximum, you see, in the graph. And it, as you are approaching further away, it is coming down, it is coming down, it is coming down.
Oh, I see.
You see that? So as you approach farther away from the Earth, this thing goes down. But at the surface of the Earth, the gravitational is the acceleration, the gravitational field strength is 9.8 meter per second square. What does this mean? This means that, for example, I am on the Earth. Okay. Now, today I am playing frisbee or something, whatever, and I throw it. And let's say that object is over here. Now, Earth is trying to pull that object down. While trying to pull it down, it will apply some force. That force will create some acceleration, that this will be that acceleration. As a result of this acceleration, what will happen? As the ball is approaching back to the Earth, its velocity goes on increasing at the rate
Oh,
of 9.8 meter per second every second. That is what the real crux of this whole thing, you see. So for example, you have left the ball over here. It is at rest. Now it starts moving towards the ground. After 1 second, the velocity will become 9.8. Further 1 second more, it will become 9.8 times 2, 9.8 times 3. That's how the velocity goes on increasing as it will hit the ground,
oh, okay, I see.
right?
Yeah.
So you might
So,
have heard that near the beaches, there are large, tall coconut trees. And there are two major reasons of people having mishaps over there. One is they are doing water sports and they get drowned or something like that. The other is they are resting under the tree and a coconut falls on their head. Right? While the coconut is coming down, that coconut is continuously accelerating. So larger the height of the tree, the larger the impact of the injury they're gonna have on their head, because it will strike with a larger velocity,
oh, okay, I see.
isn't it? So that is what the impact of G is. Okay. Now, how do I define it? For example, this is Earth. Let's say the mass of Earth is me, and this is a body. The mass of this body is small m. This is a small body. And let's say the distance between the center of the earth and the body is small r. It is a small r. Now, what will you write the force of gravitation as? The force of gravitation will act downwards, and that will be G MEM by R square. That is the force of gravitation acting on the ball. At the same time, that small ball is putting a force on the earth also, which is of the same magnitude. Right? Now, listen to me very carefully. We will arrive at this value, that what exactly this G thing is. Okay. What is this? This is the force of gravity applied by the earth on the body of mass M. All right. Now, in the dynamic section, have you done the Newton's second law? Newton's second law is
No.
force is equals to mass times acceleration.
I've heard of it, but we haven't gone over it yet.
You did it in primary classes, right?
Yes.
You are aware of this equation. Force is equals to mass times acceleration. So if I am putting force on a body, depending on the mass, if it is a very large body, it will get a smaller acceleration. If it is a small body, it will get a larger acceleration. For the same force, right? So let's say this force is coming out to be GME M by R square. This is coming out, right? Now, this particular part, Inika, is acting like the acceleration. You see, mass times acceleration. That is what the force is, no?
Oh.
You can relate this equation to that equation. This equation is formed out of gravity. Okay, fine. No doubt about that. But every force has the same impact on a body. What is that impact? Creating acceleration. So you can relate this equation to that equation. That equation bar was F equal to ma. So this is the acceleration. Right? Now let me boil down this further. You know that the radius of the earth is a very large value.
Yes.
What is that value?
Oh, I'm sorry. I don't know the actual.
It is 6,400 kilometers. 6,400 kilometers. That is the value of the radius of the earth.
My God.
We always see earth as a flat. We never, you have never felt it like a round ball. If documentaries, movies won't have told you, you might have considered earth as flat only. But they have gone outside. They have taken a picture and they've told you that earth is round. Otherwise, do you feel in your day-to-day life, is earth round or not?
It doesn't feel like
Such
it.
a
No.
large ball, Inika, that we are like a point on that ball. So we are unable to decipher the real dimensions of that ball by our senses, through our senses, right? So that is why you see now, you know what is the height of the highest tower that is constructed on the earth? Approx idea, approx. A kilometer. A kilometer. That is Burj Khalifa. It is nearing to a kilometer.
Oh, only. Oh.
The height of the tower, the longest tower that exists on the earth, is approximating to a 1 kilometer, not more than that.
Oh.
But if you feel that on the earth, how will it look like? For example, earth has a radius of 6,400 kilometer like this. Okay. And that tower to me will appear like this, the black dot, compared to the radius of the earth. Because this is 6,400 kilometers. And on the scale, this is 1 kilometer. Are you getting the feel what I'm trying to say?
Yeah.
So when we are very close to the earth's surface, no, we can approximate this value. I know that this r will change at the distance will change. I know this. But compared to the radius of the earth, whatever distance you change is very insignificant. It's like adding 10 cents on $1,000, which doesn't make sense, right? Or it's
Yeah.
even more, like adding 10 cents on $20,000. That 20 cents are insignificant with respect to $20,000, right? So in the same way, the height that you travel on the surface, from the surface, in general, is insignificant compared to the radius of the Earth. But yeah, definitely if you are doing a rocket launch and a rocket is going upside, then it will not be till 1 kilometer. It will be going really high. That time you cannot make an approximation. That time you have to take a G value, which is constantly changing. But this time when we are closer to the Earth's surface, when close, we can take the R value as RE, which is the radius of the Earth. We can take the R value as RE. So this G value comes out to be G ME by RE square. And you place all the values, mass of the Earth, radius of the Earth, G value, you will get this value as 9.8 meters.
Okay. Oh.
Okay. So I am answering your question only, the question that you have sent me with the graph. Okay. The G value, which you are called as gravitational field strength, and I called it as acceleration due to gravity. Both are the same things. But acceleration due to gravity is giving me a better perception that what that term is causing. That term is causing a change in the velocity of the body when it is falling with a rate of 9.8 meter per second every second. Isn't it?
Okay.
This is what that is causing, right?
Mhm.
Now, but the thing that you're gonna see over here in your graph, you see a diminishing value. Why is it diminishing? Because this R thing, small r thing is increasing. As the small r thing will increase, you can yourself imagine the denominator is increasing, so the G value will come down. Can you see that?
Yes.
So what exactly that question was saying us? What is the relationship between G and the R as shown in the graph? Okay, so let us try to read the graph. At the radius of the Earth, Inika, the G value is given to us as 10, approximately 10. Correct?
Mhm.
It's an approximate 10 value. 9.8 I can approximate as 10, right? As we are
Yes.
doubling the radius, you see, this value comes out to be nearer to the 2 point something. So is it becoming 1/4 of that? Like 10, 1/4 of 10 is what? 2.5. So it is nearing to that. And as you go further, like 3 times. So with this graph, what you will do? You will do it like this. The value of 10 is occurring at RE. The value of 2 point, like here at the mid, there is 3. And here, the mid of 2 and 3 is 2.5. The value of 2.5 is occurring at a 2 RE distance. Right?
Mhm.
Could you read the graph the way I am doing?
Yes.
Perfectly okay.
Mhm.
So never hesitate to ask if you are not getting what I am explaining. Okay. So at
Yeah.
RE, the value is 10. As you made it 2 RE, the value becomes 2.5. This gives me an idea that as I am increasing RE value, the G value comes down. So it must be inversely proportional. But if RE becomes twice, if it would have been inversely proportional to RE, it should become 5 out of 10. But it is becoming 2.5. That means it is inversely proportional to the square of the RE.
Um.
So when you made RE as 2 RE, Inika, it becomes 1/4. What is 1/4 of 10? 1/4 of 10 is 2.5. You're getting the feel?
Yeah. Yes.
So
Understand.
this is how physics should go. It is not something to mugged upon. It is something you understand the concept and then you feel it using the values. Okay, so what is the answer for this? 9.8 meters per second. Correct? 9.8 meters per second. 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 9.8 meters per sec 13th one. The G value is inversely proportional to R square.
Oh,
This is the answer. As you are making R as 2R, the G value become 1/4. Okay.
okay.
Everything is fine.
Yeah, that'll make sense.
That makes sense, and that is understood also, right?
Mhm.
Now, I believe that 14th question is a really interesting question. 14th one. Okay. Now we can both do together. We can contemplate what can we do, and I'll make you do this question. 14th one. Now they are talking about construction of a new planet, which is half the density of the Earth, but 3 times the radius of the Earth. All right. So let's first consider Earth. Let's say the mass of the Earth is m and the radius of the Earth is re. What is the density? The density
One,
is m upon 4 by 3 pi re cube. This is what the density is. What is the formula for density, Nika?
4/3 pi r
Sorry?
squared. Oh, formula for density, sorry.
Yeah.
Density equals
Yeah.
mass over volume.
Perfect. Mass over volume. So 4 by 3 pi r cube is the volume of the sphere. M is the mass of that sphere. That is how you are getting the density.
Oh,
Right? No worries. Now, we are first talking about the Earth, okay? Now, what is the G value on the surface of the Earth, Inika? G capital M by RE square. This is what I have told you right now.
mm,
This is what I have explained you in the previous question, no? G ME
yes.
by RE square becomes the G multiplied by M, right? All right. Can I express this G value in terms of density? Can I do that?
Yes.
How can I do that?
Mass over
You know M by RE, in spite of I can write it as RE by RE. Can I write it like this also? Can I multiply this by RE at the top, RE at the bottom? Can I do that?
yes.
So M by RE cube can be written as G times M by RE cube will be rho into 4 by 3 pi. This is what RE cube will be. You are getting what I am saying? What have I
Yeah.
done? You're not
Can
getting
you?
it? देखो, यहाँ पे देखो. It's rho multiplied by 4 by 3 pi is equal to M by RE cube. You understand this?
Yes.
So what I am trying to construct, Inika, in this G value, which is given as G M by RE square, I am multiplying RE at the top, RE at the bottom. So anyhow, what I am trying to do, I am trying to construct this M by RE cube value. You see, M by RE cube in the G,
Okay.
because I want to fit in the density in the G, right? So I have constructed this and I have written M by RE cube as rho times 4 by 3 pi. I know 4 by 3 pi is a constant. Multiplied by RE. This is what G is. Okay. So you got G in terms of density and radius now. Initially, you were getting G in terms of mass and radius. Now you have got G in terms of density and radius. Now the question arises that why I have done this? Because this is the demand of the question. He's saying that I'm making a new planet. And the new planet in comparison to the Earth has got a density half that of the Earth. The density of that new planet is half that of the Earth. And the radius of that new planet is 3 times that the radius of the Earth. So what should be the G value for that planet? So if I know G value for Earth in terms of density and radius, I can scale up that value for that planet. You're getting my point or not?
Mm-hmm.
So that is why, Inika, I got G at the Earth surface is equals to G times 4 by 3 pi density at the Earth surface into radius at the Earth surface. This is the G at the Earth surface. But all right. So G at the Earth surface is directly proportional to the density. It is directly proportional to the radius.
Okay.
All right. Now
Mhm.
you will solve that question for me. What will be the answer for that? I have left you halfway, right? I have made a formula for you. What do you have to do? You have to construct a new planet where the density will not be rho e. Rather, it will be what? Half of rho e. Correct?
Mm-hmm.
So density will be half of rho e. And the radius will become 3 times r.
Oh.
Okay. This density will become rho e by 2. And this radius will become 3 times r. That is what they are saying in the question. You see the question in your notebook, right?
Mm-hmm.
So the final value, so this whole stuff is getting multiplied by 3 by 2. So for that planet, the value of acceleration due to gravity will be 3 by 2 times the value that is for the Earth, 1.5 times. Are you understanding this part?
Sorry, can you go over this part, the 3/2? I think I kind of understand, but
Sorry?
I think I kind of understand the 3/2 for the
You,
Earth.
okay, the last part you didn't understand.
Yeah, it's like maybe clarification.
Okay, till here is it fine?
Yes.
Till here what is happening? I am getting the G value in terms of density and radius, right?
Mm-hmm.
Now, if I am saying, Inika, that I am making the density half, so my G value should become half. I am making the radius 3 times, so my G value become 3 times. If I am making both the changes, then it will become 3 by 2 times.
Oh, okay, I see, I see.
अब आ गया,
Yes.
right?
Huh.
So it is replacing those variables which we are using for the Earth for a new planet. Now what you do, just in order we will we close in a while, but what you do, this particular question, you take out your pen and paper and you address this question by yourself, the way I have done it. Then only it will become clear to you. Take out your pen and paper. Just try to arrive at G value in terms of density and radius. Okay. And then we will make the corresponding changes in that. Try it out. So when you will do it by yourself, it will be more, it will be imbibed in a better manner.
Yeah.
Yeah. Just this one you do. Have you arrived till here, Inika?
Yes, kind of.
Okay.
I think I got it. I think I.
All right, all right. Just check with this. This is the stuff that you're getting as G, capital G times
Yeah.
4 pi rho e into I.
Yes.
Then you make density half, radius 3 times. As a result
Mm-hmm.
of both, the G value becomes 3 by 2 times.
Oh, okay. Yes.
Okay.
Yes.
So what he's asking, what is the approximate G field strength on the new planet? So it will be 3 by 2 times the G value, which will be approximately 15 meter per second square. Correct?
Mm-hmm.
That is what it should be. Okay.
Mm-hmm.
What other doubts you have?
Um, right now I think everything's good.
Everything is
Hopefully.
good, right? Okay. So
Yeah.
it could be like you can mail me or you can WhatsApp me
Mm-hmm.
the coursework pattern. Okay.
Yeah.
With that pattern, we will take up the theory part because I want to be like really precise on the things. Otherwise, it could be expanded to any level, right? But
Yeah.
it has to be fulfilling to your coursework at the end of the day, right? You should get
Mm.
a good grade through this, apart from the understanding. Both should happen, right?
Yeah. Thank you.
That is
Yeah.
the objective. All right.
Yeah.
So what I will do, I will mail this notes, right?
Mm.
You give me your email ID.
Alright. Should I send it in the chat?
Yeah, yeah. Please do. Talk to Inika at the rate
Mm-hmm.
gmail. Very new idea, right?
It was actually Papa's idea.
Huh?
It was Papa's idea.
Okay. It's a very new idea. Even I will make this kind of ID now. It seems like you have that at the end of the radio shows and all, you have those addresses and the IDs, right?
Yeah, that's
Talk to
true.
RJ this and that kind of.
Uh,
Okay. All right. So these are your notes and you mailed it. and you can check.
Thank you.
Okay, all right.
Yes.
Take care. See you. Bye.
Thank you. Bye.